I'm Brian Waddell, the Director of Education and Operations for BRUCO, and today we're going to be covering chemistry and mechanics of cleaning. I like to start this session with a basic and simple overview of the pH scale. Now, the pH scale is something that many of us haven't had contact with or discussion about since sophomore chemistry. So the basic idea is this. When we measure the acidity and alkalinity of any water-based cleaning product and many of the soils that it's cleaning, we use this scale to identify it and decide what is the appropriate chemical to use on that given soil. So we look at the pH scale with our neutral, like distilled water, being about 7. As we go up on the pH scale, we get more alkaline. As we deal with products and soils lower on the pH scale, we get more acidic. So when we talk about alkalinity and acidity with our cleaners, a good place to start is thinking of a general purpose for cleaner. Most of those, and it's a bit of a generalization, but most of those sit in this range. We'll just put GP for general purpose cleaners. Now, most of those sit in that 8-9 range because, generally speaking, and a good place to start is because many of our soils sit in this general vicinity. The idea with the pH scale and the cleaners we use versus the soils we're cleaning is to try to balance those out. We want to use something to clean a soil that's on the opposite end of the pH scale. The best example of that is when we think about water deposits, calcium, magnesium, that white crusty stuff that builds up around sinks, drinking fountains, shower rooms, anywhere where water is typically found. And as that water evaporates, what it leaves behind is those minerals that are in that water. It's a common issue and a common thing that we see, but if I'm cleaning a building and I come up to a drinking fountain and I've got water spots and calcium and these buildups, and I'm using my general purpose cleaner, whatever, 409 type, to go clean up those surfaces, and I spray that drinking fountain, I get it nice and wet and saturated with my chemical, and then I wipe it and remove, or I believe I'm removing most of that soil, oftentimes a good chunk of it will disappear initially. But as that dries, as that solution and the water that was in our solution dries and evaporates off, what you'll find is, more often than not, those water stains, that buildup, that calcium buildup, will start to come back very quickly. That's because we have not removed it. We just re-wet those minerals and allowed them to disappear and not be visible. And when they're not wet anymore, when they dry, we now see that buildup is still there. That's because we're trying to use a general purpose alkaline type cleaner on an alkaline type soil. In order to properly remove a majority of those, and at least begin removing them if it's a heavy buildup, is using something on the opposite end of that pH scale. Most of the restroom cleaners and mild acids, bowl cleaners, things that we would use to remove those, depending on the area, most of them are sitting in this acidic range, and if used properly with the proper process, typically will make pretty short work of most of that buildup. Now, when we deal with the pH scale, it's not as simple as just looking at a bottle and deciding what it is. It's having an understanding of what the chemicals are, where they fit, what they're designed for, and using them in their proper area. The pH scale is also a little deceiving because as we go, let's say we've got a cleaner that's an 8 on the pH scale. As we begin to get more alkaline type cleaners, each jump on this scale, do it here, is a 10-fold jump. So I go from 8 to 9 and it is 10 times more alkaline. If I go from 8 to 10, it's 100 times more alkaline. Each jump on that pH scale represents a 10-fold increase in alkaline or acidity. The one exception to this, I should say almost all of the cleaners that we use in our buildings have a pH. The exception to that are solvents, and we'll discuss solvents and degreasers later on. So as we deal with the pH scale, I'm going to keep this up here for a bit. We'll refer back to it shortly when we discuss what's in many of these chemicals. But one other basic pillar and basic idea of cleaning that we need to keep on top of our mind no matter what the surface is, if we're cleaning carpets or tabletops or disinfecting desks, whatever it may be, is a simple acronym of TACT. Many people in the industry will refer to it as a cleaning wheel. We'll kind of discuss that shortly, but same idea, just a little different. So with the acronym TACT, each of these letters stands for one mechanism in cleaning. The best analogy that I've found to explain TACT that most everyone can relate to is washing dishes at home. So if I have a glass casserole dish, we made supper for the family and there's a big casserole dish, we've removed all of our leftovers, and we end up with all that baked on gunk that can be difficult to remove and clean. Now, we don't have a dishwasher. We're going to take that out of here. So if I walk over to the sink, small step by small step, to clean that glass casserole dish, I would walk over to my sink, and typically the first thing that I would do is turn the water on. Now when we turn the water on and we're washing something like a glass casserole dish, we want hot water, or at least significantly warmer water than room temperature. That's because in this area, the heat, the hotter water is going to help our cleaning action. It's going to clean better and break down soil better than cool water would. So our last T here is temperature. As I run my hot water, I would then get out my dish soap. Now I use Dawn dish soap, and I can tell you in my experience, the Dawn dish soap is significantly better than if I go over to Dollar General and pick up a store brand type of dish detergent. They aren't equal. They don't cut grease the same way. They don't break down soil quite the same way. It's using the right chemical for the right job. So as I take my Dawn dish soap and I start to put it in my casserole dish, there's a couple things we need to be aware of. Besides using the right chemical for the job, I can't use laundry detergent and have the same thing happen. I can't use 409 type general purpose cleaner. It's not going to clean that type of soil the same way. The next thing I need to be aware of is how much I'm using. So if I put a tiny little drop in my casserole dish, I might get some action and some things happening, but it won't have the same grease cutting power that the right amount of detergent would have. Adversely, if I take a whole bunch of Dawn dish soap and just put a giant glob in the bottom of that casserole dish, two things are going to happen. I'm going to have a giant mess of suds everywhere. And number two, I'm going to spend the next hour of my life trying to rinse all of that excess residue off of that glass dish so that I can then have it clean and free of residue and reuse it again. So the right amount of chemical is crucial. Luckily, these days, most commercial cleaning applications are done using some sort of a concentrated cleaner detergent. Some type of a concentrate that goes through a dispensing system that automatically mixes it. If we are using gallons of products, gallons of concentrates that need to be mixed, it is critical that you're using a measuring cup and all means available to you to measure that properly with the amount listed on the back of the label to ensure that A, it gets the job done that it's supposed to, and B, we're not using too much, being A, wasteful, and leaving behind residue and causing other issues down the road that we don't need that headache. So the right type of chemical, and especially in the right concentration. So we're using the right amount. So here under C, we're going to put chemical and concentration. So now I've got Dawn dish soap and warm water in my casserole dish. I've got two options at this point. I could get out my sponge or whatever I'm using to agitate and scrub and begin trying to scrub that gunk, that baked on stuff off the casserole dish. Or what I prefer to do is set it aside and allow it to soak. Give it time. So we're going to do time and agitation. Now, from personal experience, and most people have been in this situation, the more time I give that dish soap to sit and work on those soils, on that baked on crud, the better off I'm going to be when it comes time to actually have to agitate that surface and scrub. If I'm in a hurry and I'm trying to get that done right now, I certainly can, but without giving it time to work, I'm going to have to spend more time scrubbing. So that's where the cleaning wheel discussion of this comes in. Very simply, if I want to get a cleaning process or cleaning job completed, I have to satisfy all of these in one sense or another. The wheel will kind of show and illustrate how that applies. If I take away one of these or I dramatically reduce one of these, I have to make up for it somewhere else. So let's start with the temperature of water. I made the comment earlier that washing and soaking in hot water or very warm water is going to do more for breaking down that soil and being a little bit stronger, cleaner, stronger solution. That's true. However, in cleaning applications, commercial cleaning applications, we always recommend only mixing your chemical with cool water, room temperature to cool water. A couple things happen. Chemical gets more aggressive, but it also tends to gas off quicker if we're using hot water, which is not safe for the cleaning professionals. I don't want to be inhaling chemical fumes all day long. So we get less odor, less fumes when we're using cooler water. But also, hot water, if I'm doing floors, if I'm scrubbing my floors or mopping my floors, that hot water softens up the finish that's protecting my floor and making it easier to clean. And as I soften that up, cleaning that surface, I tend to cause damage to the floor finish or the surface coating as much as damage to the soil that I'm trying to break up and remove. So for the safety and health of you, of the cleaning professional, and the longevity, the asset preservation of taking care of the surfaces that we're cleaning, in general cleaning operation, I always recommend room temperature to cool water and not using any of that hot, warmer water, especially to mix our chemicals and go clean the building. So as I remove that T for temperature out of here, I have to make up for this somewhere. So if I have my casserole dish and I don't have hot water running, I have to either let that soak for even longer because that hot water's not there to aid that soil breakdown, or I get to spend more time and more elbow grease manually agitating that. The option of using more chemical isn't there for a number of reasons, but because I don't want to deal with the residue, the mess that chemical on its own can make, and being wasteful. So depending on what we're cleaning and what we're doing, we either are using a little bit stronger chemical maybe. When we get into some of the bowl acids, we'll discuss that a little further. There are options to use a little stronger chemical if I've got a really tough soil. If I use the right type of time, I give my chemical enough time to work, again, depending on what I'm cleaning. Maybe I can apply that solution, allow it extra time to work, and then come back over and do the manual part of that job. Or agitation. There are ways to increase agitation without just more manual labor and more elbow grease. Moving to microfiber cloths. Agitation out of microfiber versus cotton. It could be using a machine or a scrubber if we're cleaning floors. It could be some other type of mechanization if we're in a restroom or other setting. Mechanization and microfiber are the two easiest ways to increase our agitation without causing more work for the cleaning professional, and meaning more manual labor. So I typically like to get a balance of these. If I can just get the right type and maybe a little bit tougher chemical if it's a tough job, and using the right tool and mechanization to allow for more agitation without more elbow grease and manual labor parts of this. So to begin to talk about, we'll keep this here as I refer back to it a bit when we talk about what is in some of the chemicals that we use every day. The first and very, very common component of chemicals that I want to cover is surfactants. So surfactants is synthetic soap. So we don't use soap in our everyday detergents anymore. We use a synthetic version, a version of that soap that's made in a laboratory and made for that specific application. There are a number of different types of surfactants. Not critical to know them off the top of your head, but some are high sudsing, some are made to attack oil more, some like water, some don't. That's why it's critical to read the label, understand how a chemical is made, why it's designed that way, and where I should and should not be using it. But surfactants are our soap, if you will. They are the component that goes over fine soil, penetrates it, gets inside of it, breaks the bond from the surface. So as that surfactant, that detergent, penetrates the soil, whatever it may be where we're cleaning, penetrates, it'll break the bond, that whatever's holding it to that surface and keeping it stuck there. It'll break that bond, and then it emulsifies it. Emulsifying meaning it breaks it up into tiny little pieces, and then it will float it in solution. So that then as we take whatever tool we're using, our microfiber cloth, our mop, our squeegee, whatever it is, we can grab that and absorb it, pick it up, and remove it. The next basic piece or component of most commercial cleaners that we use is builders. Now, builders do a couple of things. Number one, builders help us set the pH of that chemical. The builder in most detergents is allowing us to build alkalinity depending on how much it is in there for application. So it helps us control and set our pH, but more importantly, especially in Montana, Wyoming, builders help condition the water. They help prepare the water that we mix our chemical with for application. And here's why. If we don't have builders in our general purpose detergent, whatever or our disinfectant or whatever we're mixing, without builders, we mix it with water and we get all of the impurities that are in our water up here, the calcium, the magnesium, all the extra organic stuff that's inside of the water coming out of our faucets and mixing with that solution. Our surfactants don't understand that that's anything but an organic component that needs to be attacked. Just like the organic stuff, it's programmed to go attack on a table or on a floor or desktop, whatever it may be. So that surfactant goes over and finds all those water impurities and starts attacking it and trying to break it down and using up its efficacy. So it will actually use itself up or wear itself out, attacking our water when it hasn't even been applied to the soil that we're using it for. Builders oftentimes will have a water conditioning agent to them. So before the surfactant has a chance to go over and start attacking those organic materials, the builder will go in, neutralize that end of the water that we're dealing with, all the organic stuff in there, so that we can save our surfactants for the cleaning that we want it to do, that we've designed it to go do. So our builders are critical. The other type of chemical that we tend to use on a very regular basis are acids. Again, most of our builders are up here. Most of our acids, all of our acids are down here. But it's important to understand the different types of acids and where application is appropriate. I've grabbed a few examples, some of the more common types of acids and restroom cleaners, bowl cleaners that we tend to use. And just want a brief explanation of what each of them are, where we should and should not use them, and how they can be applied. So number one, most commonly, ours is PST here. It is a phosphoric acid. Phosphoric acid is a very common and milder side acid. Many of the restroom cleaners that we use, whether it's for tub and tile, shower walls, drinking fountains, sinks, and in our bowls and urinals, will be a phosphoric acid base. Typically, percent of the acid can almost always be found pretty easily on the back of the label. You just go through and find where that phosphoric is. You can see that what the percentage is and understand the chemical that you're using. I believe it is imperative that whatever you're using on a daily basis to go clean, you should sit down, read the label, and understand what it is. The other nice thing about many of the bowl acids, because they're tough to discern the differences without sitting down and spending time reading the labels, they do tend to put where they're, but even one step further, oftentimes you'll see a small picture here. Now, the picture on our phosphoric acid, our PST cleaner, actually shows shower walls with a shower spout and some solution spraying. That is the indication to us that it is okay to use on surfaces outside of bowls and urinals. So now I can use this type of phosphoric acid cleaner on shower walls, on our drinking fountains, on our sinks, things outside of the typical bowl acid application inside our bowls and urinals. The next type, and very common acid, is hydrochloric acid. Now, both of these are hydrochloric acid. mint bowl and emulsion bowl. However, big difference. So hydrochloric acid is a step up from phosphoric and much more aggressive. So we start with mint bowl and just look at a couple things. Again, right on the label, we can see what our percentage is. So we know that our hydrogen chloride or hydrochloric acid here is 9.5%. Lower percentage than this. So if I'm just looking at percentages, this will appear to be stronger. It's not. We have to look at what type of acid we're also dealing with. 20% phosphoric versus 9% hydrochloric, and this is significantly stronger. The best indicator, again, to me on where I should use it and where it can be used and can be applied, this little picture up top, it shows just a toilet bowl with a bowl brush, saying, to me, the cleaning professional, I need to keep this product inside a bowl, inside a urinal, not out on shower walls and sinks and drinking fountains. It's too strong for that. It's too harsh for that. And using a product like this outside of the bowl or urinal that it's intended for can begin to quickly, A, damage the surfaces that we're cleaning, but B, be more harmful to me, the cleaning professional. And as we talk hydrochloric acid and percentages, the next jump up that, again, it's common, but should be used with great caution. All of these should, but especially when we get into higher acids. So we look at a hydrochloric acid that sits about 20%, significantly more than the 9% in our mint bowl cleaner. When we get into this type of acid at this percent, A, it should only be used in bowls and urinals, as the picture says. But B, it shouldn't be used every day. Bowl acids this strong are not designed to be used every single day in a cleaning application. Again, it's wasteful, but B, it's harmful to you, the cleaning worker, and possibly to your surfaces. This would be a 20% hydrochloric acid or the high teen percent hydrochloric acid. Should be reserved for maybe annual or semi-annual cleaning, or if we've got a couple areas that are really bad and get a lot of that red rust stain down on the inside of the bowls, or we've got some other type of major restoration project. When this type of product would be appropriate. Otherwise, we try to stick to the lower type acids, the lower percentage type hydrochloric acid for our daily bowl cleaning, and our phosphoric type acids for daily bowl cleaning on light soils or outside of the bowl like shower walls and sinks, etc. Now, solvents. Solvents are typically for degreasing applications. Somebody tracked in tar from the parking lot. There's other type of petroleum-based soil that we're trying to remove. Again, in most applications, unless it's an auto shop or a mechanic, solvents aren't a daily cleaning product. They're not a daily cleaning tool that we try to use. They're a very specific application, and oftentimes are the only thing that can be used to clean up petroleum-based grease and oils and tars, etc. Thank you very much. That was my chemistry and mechanics of cleaning. Again, Brian Waddell, thank you.